In this video tutorial, we'll be looking at acid-base strengths, as well as simple Ka and Kb calculations. A strong acid or a strong base is one that dissociates completely into its ions when in water. So, if you take a look at this situation over here, hydrochloric acid is considered to be strong. So if you had 100 molecules of HCl, once you place it in water, all 100 of them would break up. So you'd have no molecular HCl left over. All of it would break up completely into H plus ions and Cl minus ions. But please remember, when we say H plus ions, we really mean hydronium. So in a bucket full of hydrochloric acid, you would have 0 HCl molecules. Instead, you'll just have hydronium floating around and chlorine ions floating around. This is also true for strong bases as well. Now, looking over at weak acids instead, here we have an example of acetic acid, a weak acid, also known as, well, the active ingredient in vinegar anyway. So acetic acid is considered a weak acid because if I had 100 molecules of acetic acid, 99 of them would still stay stuck inside their molecular format. Only one of them would break up, and when one acetic acid breaks up, it releases one hydronium and one acetate ion. So when the acetic acid breaks up, very, very little of it, less than 1%, will actually break up into acetate ions and H plus ions. Most of them will still remain in their acetic acid molecular form. And that is the difference between strong versus weak acids. With weak acids, the H is still stuck in the molecule itself. Only the H's that are free and dissociated are able to chemically react. As long as they're stuck on the molecule itself, they are unable to react. So with weak acids, very few H plus ions are floating around, versus strong acids, since they release all of their H's, there are so many H plus ions floating around, ready to react. That's what gives the acid its strength. So strong acids 100% ionize, that's why we use a single-headed arrow, they 100% break up, versus weak acids only partially ionize, less than 1% break up, and so you'll have an equilibrium being established where most of it will be in the molecular form and very little of it will actually break up. So make sure you're using the right arrow type in your chemical equations. If it's a strong acid or a strong base, make sure you're using the single-headed arrow to show that it 100% dissociates or ionizes. While on the other hand, if it is a weak acid or a weak base, make sure you're using the equilibrium instead. Now, be aware, just because something is concentrated doesn't mean it's strong, and vice versa. Just because it's dilute doesn't mean it's weak. So in this situation, we see a very dilute solution. It's dilute because there's very few molecules floating around. It's not very crowded. However, if you look at it, every single one of these molecules has broken up completely. There are no molecules still stuck together. Therefore, we consider it to be a strong acid. So here we have a strong but dilute acid. Over here, we have all these ions crowded together, and that makes it a concentrated solution. You'll also notice that they are all ions. Every molecule is ionized. There are no molecules left. So that makes it a strong acid. Now over here we have a dilute solution again because it's not very crowded. But notice how two of them remain in their molecular form. Only one of them broke up into their ions. So that makes this a weak and dilute solution. Here we have another crowded solution. That makes it a concentrated solution, but again, very few of them are in their ion format. Most of them are stuck in their molecular format, so that makes it a weak but concentrated solution. All right, so just make sure you know the difference between concentrated versus strong, weak versus dilute. They are not the same thing. One refers to how well it dissociates, how well it breaks up. The other one refers to how concentrated, how many moles per liter, how crowded the solution is. All right, so how do we know which acids are strong and which ones are weak? Well, we memorize them. So for this course, you'll only have to worry about the 6 strong acids. And here is the story I used to remember them. I brought chlorine into the forest. I don't know why, but I just did. Unfortunately, I fell, I tripped, and I spilled all the chlorine everywhere. It was an ecological disaster, killed off all the trees. I come back a few years later to check on the health of the forest. Are the trees growing back? Are they all healthy again? No. So far, so for. No trees are growing. No threes. Only clovers, clovors, are growing in my forest. Alright, so that stupid little story has just helped you memorize the 6 strong acids, because now all you have to do is just add in the hydrogen, hydroiodic acid, hydrobromic acid, hydrochloric acid, this one's an H2SO4, sulfuric acid, nitric acid, and perchloric acid. Alright, so anytime you're dealing with these 6 strong acids, make sure you use the single-headed arrow because they will 100% ionize into their proton that release and whatever anion happens to be attached to the end. Any other acid that's not listed here, you can consider to be a weak acid, right? And so weak acids, they must use their equilibrium arrow, looking like this. I like to draw my arrows like this to show that less than 1% will break up into their H plus ions and whatever anion happens to be, whereas more than 99% will stay in their molecular format where the H is still stuck to the molecule, unable to release their ions out into the solution, thus making them weak. For strong bases, there's no need to memorize a story. At that point, it's just essentially the group 1 and group 2 hydroxide. So anyone in group 1 that's a hydroxide, so lithium hydroxide, sodium hydroxide, potassium hydroxide, or any group 2 elements that are hydroxides, like beryllium hydroxide, magnesium hydroxide, calcium hydroxide, etc., etc. Group 1 and 2 hydroxides are considered to be strong. So these strong bases are going to have the single-headed arrow again, 100% breaking up into whatever cation they are, and then the hydroxide ion behind that. Now, the only trick to all of this is that some group 2 hydroxides are insoluble. So what it means is that although they are strong bases, these group 2 hydroxides, some of them don't dissolve well in water. So what I mean is, when you dissolve something, it describes how well the solvent breaks up the solute. You would consult your KSB values to see how well it dissolves. Let's take a look at sugar, for instance. Sugar dissolves very well. It will go from a solid into an aqueous solution pretty easily. Now, when you dissolve sugar, unlike with an ionic compound or an acid where both will release ions through ionization or dissociation, sugar molecules do not release ions. So notice how this sugar crystal is made of a bunch of sugar molecules stuck together. When water dissolves the sugar, it doesn't rip it apart ion by ion. It pulls the entire sugar molecule itself out and surrounds it. So one more time, sugar dissolves very well. It's got a high KSB value. However, after that, it will not dissociate. It will not ionize. It will not release any ions. With hydrogen chloride, it also has a very high KSB value, meaning it dissolves very well in water, going from solid to an aqueous solution. From there, hydrochloric acid can then ionize fully into H plus ions and Cl minus ions. So you would never have HCl molecules stuck together. Those would not exist in an aqueous solution. Instead, they would completely 100% break up in H plus and Cl minus, and that's why HCl is considered to be a strong acid, because it ionizes fully. With acetic acid, again, very soluble, high KSB value, so it will dissolve quite readily in water. But because it's a weak acid, by definition, weak acids do not break up very well, do not ionize very well. Most of the molecules, more than 99%, will be stuck in the molecular form with H still attached to the acetate ion. Very, very few, less than 1%, will break up into the ions acetate and H+. And that's what makes the acetic acid a very weak acid. Now, calcium hydroxide is a group 2 hydroxide. And as I mentioned before, group 2 hydroxides are strong bases. But the problem with calcium hydroxide is that it's got a very low KSB value. It does not want to dissolve very well in water. More than 99% will stay stuck in this format as a solid. Less than 1% will actually turn into aqueous solution. However, of the type, or of the small amount that actually dissolves, 100% of these guys will break up into these ions. All right? So that means the calcium hydroxide actually does not exist in solution, because 100% of them will break up directly into the calcium ion and the 2 hydroxide ions. Just like with HCl, you will not see any HCl floating around solution because it's a strong acid. 100% of it will break up into H plus and Cl minus ions. With aluminum hydroxide, its KSB value is very, very low, so it does not dissolve well in water. Less than 1% will actually dissolve in the water. So you'll have a bunch of powder sitting at the bottom of your beaker. But of the aluminum hydroxide that actually does end up dissolving in water, because it's a weak base, it's not a group 1 or 2 hydroxide, it's a weak base, less than 1% of 1% will actually break up into its ions at that point. So to recap, sugar dissolves very well in water, but it does not dissociate or ionize. Hydrochloric acid dissolves very well in water, and it dissociates fully into its ions. Acetic acid also dissolves very well in water, but it does not dissociate well into its ions. Calcium hydroxide does not dissolve very well, but it does dissociate fully into its ions, the small number that actually does dissolve. And then finally, the aluminum hydroxide doesn't dissolve very well in water, and the part that does dissolve doesn't dissociate well into its ions either. Because weak acids and weak bases do not completely ionize or completely dissociate, we can write an equilibrium expression to describe how well they break up. Instead of saying products over reactants, however, we will say how much ionized versus how much remained unionized, or how much dissociated versus how much did not dissociate. Now, strong acids and strong bases will have very high Ka and Kb values. Because they fully dissociate or ionize, you're going to have large values in your numerator. Conversely, weak acids and weak bases, they will have very low Ka, Kb values because the denominator will be much bigger because most of them will still stay in their molecular format. Now, if you're dealing with conjugate acid-base pairs, we can convert between Ka and Kb using this lovely equation over here. Ka times Kb equals Kw. If you recall, Kw is the ion product constant for water, which is 1 times 10 to the power negative 14 under standard conditions. But don't worry about this calculation for now. It'll become more useful to us once we get to the acid-base titration calculations. Now, another way to represent how well an acid or a base breaks up, instead of using Ka or Kb, we can use something called percent dissociation. And these are the equations to show us how well an acid will break up. So just take the concentration of what actually broke up, divide by the concentration of what is left over that didn't break up, multiplied by 100%. Now, the last thing we want to talk about is polyprotic acids. If you recall, according to the Bronsted-Lowry definition, an acid is defined as a proton donator. So whichever compound releases the H+ ion is considered to be an acid. However, some acids can release more than one proton. So for instance, acetic acid over here is considered to be monoprotic. Right? Monoprotic, remember protic sounds like proton, and a proton is basically an H+ ion. So with acetic acid, it can release this one H. And that's why it's called monoprotic. Now some students go, well, doesn't have these other H's, why can't these H's be released? This is known as an acetate ion. It's a polyatomic ion. Polyatomic ions are those groupings of atoms that tend to be very stable together, and because they're very stable together, they tend to react as a group. So this acetate ion very rarely breaks up during chemical reactions. So this H is integral to its stability and cannot just be released as an acid proton. All right, so only this one H at the very end can be released, and that's why we typically write acetic acid as CH3COOH to keep this H and these H's separate so that we know it's just this H that's able to be released and not these H's. Sulfuric acid and phosphoric acid, on the other hand, are considered to be polyprotic. Specifically, sulfuric acid is known to be diprotic. Di is the prefix for 2 because the sulfuric acid can release 2 H's. It releases one H here, and then from here, HSO4, it can be released a second time. Phosphoric acid is triprotic because it can release 3 H's. It releases an H over here, then it's got 2 left over, which can then be done again. Then it's got 1 left over, which can be done again. Now, if you recall, sulfuric acid is considered to be a strong acid. It's one of the 6 strong acids you have to memorize. Because it's a strong acid, we don't write an equilibrium arrow. We draw a single-headed arrow to show that it completely ionizes. So the H2SO4 breaks up into H+ ions and HSO4. However, HSO4 is not on our list of strong acids. It's considered to be a weak acid. So from HSO4 breaking up into these guys, this requires an equilibrium arrow because this is unlikely to occur. So when H2SO4 dissociates, we call this the first dissociation constant, Ka1. Notice how Ka1 is a very large number because we know that this will completely break up. On the other hand, the second dissociation constant, Ka2, much smaller than Ka1. So going from HSO4 into SO4, that's very unlikely to occur. So if I had a beaker of sulfuric acid, the most common ion or molecule floating around my solution would be H+, because you have a lot of H+ floating around here, and you have some H+ being released over here. The next most common ion you'll have floating around the solution would be HSO4, followed by sulfate, because to get to the sulfate level, you'd have to break up a second time, and that is very difficult to do. Finally, you would have 0 H2SO4s, because all of them broke up during the dissociation. And so this would be the increasing concentration of your ions in solution. With phosphoric acid, because it's weak, very little of it breaks up right off the bat. So the first dissociation constant, very small. But then to get to this next step, it's less and less and less likely. So if each time you're breaking up and less than 1% actually breaks up, then that means in order to get to this step over here, only 1% of 1% of 1% will finally make it to the phosphate level. So that's why the concentration of ions in a solution of phosphoric acid in increasing order would be this. Most of the molecules will be H3PO4 still stuck together because very few of them broke up. Then the next common ion would be H plus ions because they're released here, here, and here, followed by the H2PO4, HPO4, and then finally the phosphate, which is the least likely ion to be floating around your solution. Alright, so typically each dissociation has its own unique equilibrium constant, K1, K2, K3, and they progressively decrease as you go along. Alright, so let's give this question a try. Press pause. When you're ready, press play, and we'll take it up together. Alright, so this question is asking you to find the Ka for acetic acid. So we need to know how well does the acetic acid break up. So concentration of what is ionized divided by the concentration of what remains unionized. Now it says the concentration for the acetic acid is 0.1 moles per liter. So I'm just going to fill that in over here. And because it's initially, it hasn't had a chance to break up yet, I can write down 0 and 0. None of the acetate or H plus ions are present in the solution yet. Obviously, the equilibrium has to shift to the right. There's no choice. It can't go backwards without any acetate or H plus ions present. So this is going to be a minus X value, and this is going to be a plus X and a plus X. Everything is a 1 to 1 to 1 ratio. Make sure it's all balanced. It is a balanced equation already. And therefore, at equilibrium, I'll have 0.1 minus X, X, and X for this. Now, it also mentions that the solution pH at equilibrium is 2.9. Since the pH is 2.9, I can use this equation to solve for the hydronium concentration and then plug that value in here. Therefore, X is equal to 1.26 times 10 to the power negative 3. Since it's a 1-to-1 ratio, for every one H plus ion that's produced, one acetate is produced. So if I produce this many H pluses, I must have produced this many acetate ions as well. Since 0 plus X equals to 1.26 times 10 to the power negative 3, I know what X is. I can then fill out the rest of the chart, substitute it into my Ka equilibrium expression, punch that in, and therefore your Ka value is 1.6 times 10 to the power negative 5. Let's double check to make sure it makes sense. Acetic acid is a weak acid, therefore its Ka value should be small, and yes, it is quite small. Alright, moving on ahead to the next question. Once again, press pause. When you're ready, press play, and we will take it up together. Alright, so the question's asked me to calculate the pH for this solution. And the equation I'm going to use is pH is equal to negative log of the H plus concentration. So what I need to do is find and solve for the H plus concentration and plug it in here. It says that the solution concentration is 0.5 molar for HClO, so I'm going to write that in 0.5 molar. And of course, since it's an initial situation, it hasn't had a chance to break up or ionize into H plus or ClO minus yet, so I'm going to write 0 and 0. Once again, the reaction can't go in reverse. It has to go forward. So therefore, this is going to be a minus X plus X and a plus X. Just make sure the equation is balanced. It is, in this case, 1 to 1 to 1 ratio, so I can leave the coefficients as a 1. And therefore, my equilibrium values will be 0.5 minus X, X, and an X. The question goes on to say that the Ka value for this acid is 3 times 10 to the power negative 8. So I'm going to set up the equilibrium expression, ionized component divided by the unionized component. I can then substitute the values into the equation and solve for X. Now I'm going to use the assumption rule to simplify the equation, make it easier for me to calculate it. If you recall the assumption rule, take the initial concentration, divide it by the Ka value. If the number is much greater than 1,000, that means X is negligible. So 0.5 minus a negligible number might as well be 0.5, which simplifies my equation into this, where I take away the X. Once I solve for X, which equals to 1.2 times 10 to the power negative 4, I can then punch in the X value into the pH equation, and I can get a pH of 3.9. Part B of the question asks you to calculate the percent dissociation. Here's the equation for it. So what percentage of the HClO will actually break up? So take what broke up, divide by what was the initial concentration, multiply by 100%. So I just take the values of what broke up, there it is, divide by the initial concentration, multiply by 100%, and it looks like 0.024% of HClO will break up and dissociate into ions. Let's see if our answer makes sense. HClO is a weak acid. It's not one of our strong acids, not on the list. So therefore, its percent dissociation should be very, very small, less than 1%, and it definitely is less than 1%. Alright, so that concludes our video tutorial on strong and weak acids and simple Ka-Kb calculations.